First time.
Hey, Matt. Did she hear you?
Jackie, do you have anything to say?
Wanna
Hi,
say?
Jackie.
Jacqueline. Hey, Daddy.
Yes, she can hear. Basically, it just records the voices and then whatever I mark on the tablet. Oh, you want to share the school name?
Oh, yeah. It's okay. It's all over Twitter already.
She'll probably hear about it before she looks at this screencast.
It's already all over Twitter.
Probably. Okay. So, differentiability. Ah,
Will we need a spot after?
we'll see. Okay, so there are certain times that the derivative does not exist. Okay? Okay. So you need to be able to look at a graph or an equation and figure out which reason it is. So is it a corner? Is it a cusp, a vertical tangent, or a discontinuity? These are the four
Where they don't exist.
where they don't exist. So actually, I'm going to look at the discontinuity first because I think that came up in our homework assignment. This is an example. So from the left and from the right, they have the same slope. These both have a slope of 0. But because there's a jump discontinuity, it doesn't have a derivative. So in order to have a derivative, we need to make sure that it's continuous. Okay, so discontinuity won't work. And that's true if it's a removable discontinuity. It could be a jump discontinuity, an asymptote, it doesn't matter. Any of those would make it not have a derivative at those places. Oops. Okay, so the very top we have a corner. And a corner is exactly what you would think it looks like. Looks like a corner. Okay. Specifically, it's where the one-sided derivatives differ. So this particular example here, if we compare the left, so for example, if I do, I'm just going to write out the abbreviation. So if I look at the derivative from the left, what would that be? What's the slope? -1. And the derivative from the right, +1. So whenever we have a left and a right-hand derivative that are not the same, it's a corner. So it doesn't necessarily have to be straight lines. There could be like a curved line, two curved lines coming together. But if these two slopes are different values, it's a corner. Make sense? Next one. Okay, so cusp and vertical tangent are a little more complicated. So cusp, think of like, like you think of like the top of a heart where it goes in and then goes, right, it curves inward. This is where the slopes of the secants approach infinity from one side and negative infinity from the other. So basically what I'm saying is the derivative of the function from the left. So kind of imagine your tangent line. Okay, it's following the curve. And what happens to, not the actual value, but the slope of this? What's the slope? This is a negative slope, so it's approaching negative infinity. Do you see that?
Line and okay.
Well, this is how it's defined as. You basically have to have, a cusp is something very specific. Why is it not erasing? The cusp has to approach negative infinity from one side and positive infinity from the other side. The slopes that it, not the actual value. The actual value is approaching 0, but I'm talking about the slope. Right, it looks like it's becoming a vertical line. And so from here, from the right, there's a positive slope, and the slope is approaching positive infinity. What's that? The slope. Okay, picture here, you can approximate that slope. It's maybe, I don't know, 1/3. And then as we go here, it's 1. And then the slope is 2, 3, 4, 5. And what happens when it gets more, when it looks more like a vertical line, our slope, it's never gonna actually become vertical. Okay, it's not possible, but it becomes, the slope becomes increasingly large without bound. Make sense? That's your cusp.
Increasing,
So it's kind of like,
negative infinity is like approaching like undefined, but.
yeah, so these slopes, one's negative, one's positive, but they're becoming more and more vertical. So the actual slope value is approaching infinity from one side and negative infinity from the other side. That's a cusp. Just go with it. It's like vertical tangent. Okay, vertical tangent is when they both approach positive infinity or negative infinity from both sides. So this example, oops, sorry, not the limit. I keep writing limit. What's the derivative from the left? So imagine here's my tangent line, and what's happening to the slopes? See how it's approaching a vertical tangent right in the middle? Okay, so it goes like this. When it has a vertical tangent right in the middle, then that is not going to be differentiable. So here, from the left and the right, they both approach positive. So whenever they both approach positive infinity or both approach negative infinity, that's a vertical tangent. Elijah?
These are just all the rules for limits. When limits exist.
Yeah.
It has to be continuous, can't be infinity, can't be an equal.
Right. So when you're talking about derivatives, when you're talking about slopes, slopes can't be undefined, right? You can't have a vertical line. If you have a vertical line, it looks like this, where the slopes are approaching positive or negative infinity. So those fail to exist. But you have to know the difference between the two. That's why I said these two are the most difficult. When it's discontinuous, that's easy. That's the easiest one. A corner is probably second easiest because you can just see that they don't, usually those would be like your piecewise functions would be a corner. So it's approaching from the left and the right, but different slopes. These two are something very specific where from one side is approaching a slope of negative infinity, the other side is approaching a slope of positive infinity, and then here they're both approaching positive infinity. That's a vertical tangent. So you just need to be able to figure out which one it is. Do you have questions? Okay. Let's take a look at our example here. Okay, so we're going to compare the right-hand and left-hand derivatives to show that the function is not differentiable at point P. Find all points where the f is not differentiable. What kind of point does this look like? What do you think? Okay, so it looks kind of like a cusp, but a cusp would have to approach positive infinity and negative infinity from the left and right. So let's compare. Let's look at the derivative. Let's do the derivative of 1, because we're specifically looking at 1. Everywhere else it's differentiable. Let's look at 1 from the left. So that's going to be the limit. H approaches 0 from the left. Okay, so we're looking at the y equals x squared part. So I have 1 plus h squared minus 1 squared all over h. So what do we have? 1 plus 2h plus h squared minus 1. So 2h plus h squared over h. Factor out the h. What do we get? Equals 2. Okay. And then let's check from the right. So the limit as h approaches 0 from the right. Now we have the function y equals 1 over x. Again, we can plug in 1. So it's going to be 1 over 1 plus h minus 1 over 1 all over h. You okay with that? That's the definition from one side, the left side and the right side. How would we simplify this? Yeah, just make this 1 plus h over 1 plus h maybe, just so we have a common denominator. So now what? We have 1 minus h over 1 plus h times 1 over h.
If we multiply by 8,
The negative.
Well,
one.
no, I took the 1 over 1 and I just made it 1 plus h over 1 plus h.
Oh, okay.
So I had a common denominator,
Yeah.
and that's going to be 1 minus h. So the ones are going to cancel, I'll have negative h, and this h will cancel to give us a negative 1 over 1. So my slope is negative 1. So we can see, because this result was 2 and this one was negative 1, notice it looks like, remember how you said it first looks kind of like a cusp? It's not a cusp because we didn't get positive or negative infinity for our results. So that's how we know it has to be. This is a corner, even though I didn't ask that question, but this is a corner. So it's not differentiable. At x equals 1. So it says find all points. That's the only place. Everywhere else here, it will be differentiable because it's a parabola, so it's continuous. It's going to be, whenever it's a smooth, continuous curve without any, like the corners, and it can't be a cube root, then it's pretty much going to be differentiable everywhere. Let's look at, oh, okay. So one of the things that we talk about is differentiability implies local linearity. When we take a graph, so here's a graph of negative x minus 3 squared plus 4. If I zoom in, getting closer and closer to x equals 3, what happens when you zoom in and zoom in and zoom in on a graph? It gets, yeah, it's going to look more and more like a line. So picture these lines. So wherever you zoom in, that's like a tangent line. So if I zoomed in on another spot, say, 2, if I kept zooming in, zooming in, zooming in, eventually it's going to look like a straight line. Okay, and that's what our derivative, that's what our tangent would be, and that slope of that tangent is our derivative. Okay. Okay, so calculators. Calculators. There are a number of different ways that we can use our calculator to evaluate derivatives. So now you have a way to check. I'm going to show you a number.
You can all the derivative problems be in the calculator section or in back.
Well, I'm going to the next lesson is actually all of our shortcuts. So after this next quiz, we'll have all the shortcuts. You'll have your calculators to check. Let's take a look at, let's say we're given x squared, and I want you to find the derivative at 2. That means what's the slope of the tangent? Again, we can kind of picture if you had x squared, right? And then I want to look at, 2. What is that? What is that derivative? What is that slope? Okay, first method, using the math button. So go ahead on your calculators.
How far is the microphone pick up? Like, can you hear something that happened in the back of the room?
Yeah. Well, if it's loud enough. You can, I will post it. You guys will be able to see. Why does it keep doing that? Okay. I know. All right, we're good? Oh, I don't want you to put it into the graph yet.
Yeah, I was there. I was really
Okay, so we're going to press the math button. And if you go down, do you see where it says n deriv? That is the derivative. So we're going to type the number 8. Okay. Now, depending on which calculator you have, will depend on how this shows up. Does it show up like this on yours? Yeah?
on
Okay,
that's
so.
Jackie's the one who has the older calculator.
Oh, sorry, guys. I'll have to show you later. It's actually down here.
You know,
I put here,
you
or
know
older
the
model.
SmartView software actually
You can
change the
update it.
calculator. You can make it the older calculator.
I don't want to. Why would I want to do that?
So Jackie can see what's going
Oh,
on.
I'll work with her on it.
Okay.
Alright, so first thing we need to do is we need to put ddx. So it tells us we're taking the derivative with respect to x. In this class, we will always put an x, just so you know. You don't need to worry about putting a y or any other variable in here, just put x.
What number does it have stored as the variable though? This doesn't have variables. Doesn't have
No,
stored.
we're using x as our variable, but we're gonna be plugging in the 2.
Ah.
Okay, next, we wanna make it look like this. So x squared is what we put in the parentheses. And then we have to just press over. This line right here means evaluated at. So this means, the first part means take the derivative of x squared. Evaluated at x equals 2. Press enter. Here we get 4.
Oh, okay.
So that means f prime of 2 is equal to 4. Good. Okay, next we can do it by graphing. So let's take a look. If you go to your y equals and you type in x squared and graph it. Good. Now there's actually 2 things that we could do here, but I'm going to show you the second and then the trace button. That's what you're going to do next. So second, trace. So in pre-calculus or algebra 2, you've already learned about value. You found the zeros, you found the minimum, the maximum, you've done intersection.
Can you leave the phone at the bottom?
And you see number 6 says dy dx. Okay.
Second.
Number 6, second trace. Now, it's going to automatically just put the cursor at 0, 0. You just need to type in the number that you want to evaluate it at. So I want to evaluate it at x equals 2, so I'm just going to type in 2. Just type 2. Just put the 2 in. And then press enter. And dy dx is 4. Isn't that what we got previously? Okay. There's one more thing.
I like this.
Isn't this nice? So you can get a visual, so you can see, just to make sure, yes, I wanted it at 2. It will even give you your y coordinate. So you can check, like, for example, if you had to write the equation of the tangent line, it gave you, you have to put in the x value. It'll find your y value, it'll find your slope. So hopefully from that information, you give you the slope, the equation of the tangent. Now, there's one more thing you can do. You can actually draw the tangent line. Okay, I didn't put this in here, but if you see under where it says, or above where it says program, you see that? So second, we're going to press the second.
Is it slope 4?
The slope is 4.
Is it also
Oh.
y value?
Go second, program. And we are going to draw the tangent. It didn't, oh, hold on, wait, let me make sure I put it in correctly. So,
Whoa!
What? That's so cool. I did love it.
press enter, and there is my tangent, and it gives you, so, oh, that's weird, did it give you the equation?
Yeah.
Yeah, it's just a weird, like, the numbers that they gave you, wasn't it?
Is the y
numbers?
but I put in x plus I actually plus 2. Because it wasn't set at 2.
Yeah, see, and this is weird because it's not rounding to 4 for the slope.
Yes, yeah,
I think it's an it's gonna, sometimes it gives you exact, I've gotten exact.
Mine gave me
before.
4x minus.
Yeah,
Yeah, that's weird that mine didn't do that, since I've used the 84 before.
I think it is plus 2.
Check your mode.
Oh, because I have x
Oh,
equals
did you-
1.9.
Yeah, you dragged the
did I drag it
cursor.
back?
You dragged the cursor. You didn't have
No, mine did the same thing.
Wait,
No, because it started at 1.9. Yeah, they're right.
Okay, hold on.
It started at 2, at the point that the tangent sheet on.
I'm pretty sure I saw you drag your cursor, but.
Okay, I'll double check.
And then after we get 2 now, and then.
Yeah, thank you.
Calculator's not gonna talk, Adam.
Calculator is friend.
Oh, no, but you know what? It's weird because when I went back to that screen, it was automatically that decimal.
Yeah, it's,
Okay.
I don't know why, but if you set it to 2, it works.
All right, guys, so we will continue the next class.
You just tried to do it homework.
Yeah, definitely try to do.
So basically, the moral of the story is everything we have to do by hand, we could have done by calculator.